So my name is Denzil. I work in the Hyperscale team. Hyperscale is kind of a relatively new tier in Azure SQL database family, which is the PaaS services. So today we will go through kind of some of the benefits and use cases. What's different about Hyperscale versus the other tiers of SQL Server. We'll dig into the architecture of Hyperscale, and feel free to ask questions along the way. Brody, you can interject if I don't see it. Feel free to interrupt me. No worries. We'll see a few demos. We'll talk about migration, both from kind of on-prem and or VM and across different tiers in Azure. We'll look at a few performance best practices, and then we'll talk about a few roadmap items. The joys of the cloud is we can release things every couple months versus actually waiting for a release. So what does Hyperscale solve? Effectively, there are challenges with very large databases, in particular on the cloud, right? So there are certain operations that take a long time. Things like and you got to size for peaks too. So when you're sizing your workload and you're buying some hardware resources, you're sizing for peaks. There are operations that take a long time, like backups if you get into the terabyte ranges. There are ongoing operations that degrade performance, and it can be painful. Current tiers of Azure SQL Database have some size limits around them, and that's why Hyperscale was actually designed. As your size of data grows, provisioning storage can be painful, and scaling compute is not non-trivial. So that's some of the value prop, or that's what Hyperscale is solving in many cases. So some of the benefits and use cases from an availability and performance perspective. The first one is a rapid scale out of data. So you can scale up and down compute irrespective of data size in constant time. So you can go from 8 cores to 80 cores, from one replica to 3 replicas in less than a minute. Yes, any scale up and scale down will take SQL Server down and up, but it's a matter of seconds, if you will. Then the other benefit is a high data ingestion rate, which is different than other Azure tiers. This is not simple recovery model like you can do on-prem because of some of the SLA benefits. As part of the PaaS service, you get an SLA and you get a redundancy, and setting up HADR is just a click of a button, and in 60 seconds you can have a replica or two. So ingestion rate, this is comparing Hyperscale with other compute tiers. On business critical or general purpose, every slow or tier has some sizes associated with it: size of compute, size of memory, log generation rate. In Hyperscale, the data ingestion rate is the same regardless of compute size. Backups and restores are just snapshots. So if you think of a SAN and SAN snapshots, you can look at it the same way. So it's Azure storage, snapshots. So the backup and restore process is a constant time. So whether it's 1 terabyte or 10 terabytes or 15 terabytes, your restore should be within the 20-minute range. And we'll talk about that in a little bit more detail. Then you can scale out reads. On Hyperscale, you can go up to 4 replicas, and then there are more which are coming with some of the previews called name replicas. Then you get better performance. If you look across the Azure SQL tiers, you have general purpose, you have business critical, and you have Hyperscale. So definitely better performance than standard or general purpose. On the business critical tier, you could get equivalent performance, except for one aspect today, which is log latency. If you want 1 millisecond of very low log latency or commit latency, business critical is still a little faster than Hyperscale. Then you have SLA from 99.9 to 99.99, depending on the number of replicas. Even with a single replica, because of the separation of storage and compute, you can get a 99.9 SLA. Even on an unexpected failure, we spin up new compute and we'll fail over to that replica. So that's the availability and performance. From a size perspective, we support up to 100 terabytes. And there is auto scaling for data and logs. So you never have to actually do storage capacity management from that perspective. We grow the data as needed, and there is the Xlog service, which we'll talk about in a bit, which has an infinite log abstraction. So common use cases, what can we use this for? OLTP databases of any size at a better price performance ratio than business critical or premium. It is also used for real-time or HTAP or workloads. So you want to kind of do the real-time analytics, if you will. We have great support within the engine with column store, indexes to enable that scenario as well. It's also used for operational data stores, for data marts, and for SMP, not MPP data warehouses. So we have Synapse or Azure DW. So if you're coming from a Teradata or any of the MPP or massively parallel processing compute scenarios, then Synapse is the way to go. If you're coming from SMP, given the compatibility with SQL Server, I mean, Hyperscale is can be a choice without changing a whole lot at all. And then data ingestion at scale, you have IoT and logs as well, because of the size limits of 100 terabytes, we've seen quite a few IoT workloads as well. So some of the new scenarios which it brings about, this is a common scenario nowadays where you have an event source. It can be from on-prem here, or it can be devices in an IoT scenario. They're feeding data to Event Hub. And then, data can be pulled from Event Hub in one of many ways. If you want fully PaaS service, it can be functions or Databricks, where you can ingest micro batches, which is, in the hundred to thousands of rows, in a single micro batch and push it into Hyperscale. Right, so a lot of customers have this scenario, and this is, I mean, the OLTP scenario is well known, so I'm not going to go into that, for sure. And so there are benefits here in terms of being able to spawn 4 read replicas and ingesting into one and having some amount of read workload. But as you need to actually scale out your reads, you can go up to 4 replicas. So this is a customer case actually which they've done, where they were doing then models on top of that data to do real, near real-time fraud detection, right? And this same data, since it's an Event Hub, can go to an MPP system like Synapse for more of the larger warehouse types queries, and it can be data from multiple sources as well. The other scenario is data marts. Prior on the other Azure SQL DB tiers, the size was a restriction for this, right? And this is in conjunction with column store. Again, this is more of your ETL or batch loads. It's not so much micro batches or data trickling in all the time. Rather, it's kind of a scheduled batch, if you will. So some of your compute engines like Azure Data Factory or Spark, can push this data either into a MPP warehouse like Synapse or into Hyperscale, right? And Hyperscale has multiple scenarios. Again, you can ingest into one, query of many, or you can do in the truncate and load scenario, which some customers still do today, because their systems are not set up for incremental. You can do things like load and swap the database once the load is done, kind of the snapshot approach, if you will. So that's databases in this size. We have customers who are doing 5 to 20 terabytes range, and of course for this, depending on the type of queries, then you model the data appropriately with column store or row store. One thing to note on ingest itself, if you're ingesting into column store and if you land on compressed row groups, you're optimizing that log generation rate so you can ingest more in a quicker format. Here are some case studies for customers who have adopted. I'm not going to go over these in details, but just have links in the deck, which I will share at the end of this. So having said that, let's look at architecture. From an architecture perspective, you can look at Hyperscale as a distributed system with 3 main components. You have the compute component, which is the endpoint that users connect to, right? And this can be the primary, which is a read and write replica, or it can be the read-only replicas. And then you have the second component, which is the log service. And this is where all your write activity happens to. It's this blue line. So write activity happens to the log service. There is no write actually from compute to this layer. All the write goes to the log service, and it's the job of the log service to distribute all these transactions to other actors in the system. And then you have two levels of caching. This compute also has a local SSD cache so that you don't do remote reads all the time. And then you have two other layers of caching. One is called the page servers. Page servers, you can look at the page servers as a remote SSD cache. And then you have long-term retention with Azure storage, which is more of the slow Azure storage. So you never necessarily read directly from here or write to here. So digging into a little bit more detail, the first thing is, I mean, you have separation of, as you can see, compute and all your storage layers, right? The log pathway is in red, the data pathway is in green. So any transactions coming in go to the log service. It's an externalized log service. And then this log service in turn ships these transactions to all these page servers. So page servers are your remote SSD cache, and each page server actually then has a corresponding blob in a storage account, which is Azure storage, right? And this log service also has a long-term retention blob, which is in the slow Azure storage, account. And then when we read data, if data is not in buffer pool or in the cache on the primary, we read this data from these page servers. Okay, so that's kind of the high level architecture. And then log service also is responsible of shipping some of these log records to the secondaries. So primary never talks to secondaries directly, unlike in availability groups in always on-prem. Log service actually just ships those records which are already in the secondaries cache. Anything else, the secondary can also share these set of page servers. There's redundancy at all tiers. So for example, every page server has a replica. So if one fails over, the other one takes. So actually they're in active state. Storage is encrypted at rest. You can have TDE enabled at the database, but storage is also encrypted at rest, irrespective of if you enable or don't enable TDE. And there's this protocol called RBIO, which intercepts all these IOs and makes this possible. So when you issue any IO, any read file, write file, read scatter, write gather APIs, we actually intercept that and actually do this translation to log service. So primary replica is configurable. The scale up is today up. You can go from 2 to 80 cores. The memory and local SSD is proportional to the number of cores and depends on the generation. So 80 cores have 400 and odd gigs of memory. And this services the read and write workloads. So again, primary replica has this buffer pool that we know, it's normal SQL Server. We also have a non-covering RBPX cache, which sits on the local SSD. So what is cached here are, if you touch a particular page twice in buffer pool, it's cached in RBPX. So even if it gets evicted of buffer pool, you're never doing a remote read. Right, so it's the same engine as Azure SQL Database tiers. So everything that you're familiar with from a SQL perspective still applies. Then you have the readable secondary replicas. Currently, it's the same sizing as the primary. So if you have the primary of 8 cores, the secondary is of 8 cores, so on and so forth. We are having a preview of something called named replicas, which will enable having replicas for read purposes which are a different size. Today we can go up to 4 secondaries. Application intent equal to read only will land you there from a workload perspective. If you specify in your connection string application intent equal to read only, you'll be load balanced across these primaries. The replicas are cheaper from a pricing perspective. They are at Azure hybrid pricing. So I think it's like 35 or 30, 35 to 40% off. I don't know the exact amount. It's around 35% off. And then if you have a replica in addition to the primary, your SLA goes up because they are also a hot failover target in case we have a unplanned failover. Right? So that's one thing. Then next thing is the log service. So the log service, you have to look at it as a single producer and multiple consumer model. So single producer is the primary, which writes log records to it. Multiple consumers are all the other actors in the system. This provides infinite log abstraction. You have something called the xlog process, and I'm not going to dig too much into it, but we'll look at this in a second. Then you have the landing zone. Landing zone is nothing but Azure Premium Storage. You can almost think of it as kind of a a VM on Azure, which has the data file on Azure Premium Storage, which is the log data file. This is 1 TB today. It's a P30 disk. Generally, commit latency is in the 2 to 4 millisecond range under load, right? So the way I mean the layout of the log is the same kind of as on-prem. It's a little different. There are some tweaks in terms of VLF sizes, but otherwise the layout is pretty much the same. So when you commit, actually you're not touching anything but the landing zone. Once the log record is in the landing zone, your transaction is committed. Asynchronously, we also send this to the xlog process, and this xlog process then hashes these log blocks. And why does it hash these log blocks? Because it actually does some content filtering, because then it knows that this log record is on page server 1. So I'm only going to send page server 1 the log records that belong to it, not ship all the incoming log records to every page server in the system. Similarly, if the log record is on another page server, it'll only be shipped to that page server, right? So xlog service, xlog process actually services, get log requests from replicas as well as page servers, and it hands those replicas and page servers the log to catch up, once a transaction is committed, right? And then you have long-term storage. Of course, if this was only 1 TB, then your size of log would be 1 TB. But what we do as VLFs, fill up, and these are 16 MB VLFs, we flush them or we destage them to the Azure storage, blob, if you will. And this, how long this is retained depends on a retention, whether it's 7 days of retention, which is default, which is there, or 30 days, if it's 30 days. So that's the long-term storage thing. Then you have a concept of a page server, and this is that remote SSD cache. So page servers are, if you create a new hyperscale database, they're 128 gigs per page server. There is a 1:1 correspondence between a page server and a file in sys.database files. So if you query sys.database files and you see 10 files, you have 10 page servers. If you see 100, you have 100. So effectively, for every terabyte, we have 8 page servers, right? And how do these page servers get updated? Through the xlog service, right? So it replays log to update its pages, which was in the xlog service. Each page server is covering of that 128 gigs. In other words, it has an RBPX cache, which is local SSD, and all that 128 gig of that page server will be in its local SSD or in buffer pool, and or a combination thereof. Right? So a read from compute that requires a page that it doesn't have in its buffer pool effectively communicates with the page server and gets it from here. It never goes to this long-term storage, which is actually significantly slower. So each page has its file and data storage. The other thing is page servers do offload some of the compute operations. So for example, backups, there is no resource usage on the primary or replicas because backups happen with snapshot of the page servers. So right there, you're saving some resources in terms of CPU and IO on the compute and can use those better for the user workload rather than some of the maintenance activities, if you will. Right. So checkpoints similarly, and backups are done in snapshots. We take a snapshot every 12 minutes or so, but we'll talk about that in some of the restore. And this page server also has a replica. So it's a service fabric application which runs SQL Server.exe and has a replication factor of 2. And each replica actually is independent of each other. They don't ship data within each other. Each of them is independent, and they service requests, and they run in an active way. So the compute actually maintains the quality of service to each of these replicas, and even can switch at runtime to one or the other depending on how fast one is serving requests or the other. So they also handle fault tolerance in that way. Right, and the data file itself has storage redundancy with ZRS accounts or zone redundance, storage accounts.
Okay,
So what
we have a
happens?
question.
Yep. Sure.
Will the page server be flushed periodically so when a read does not find the data, it reads from storage?
No. So page server is never flushed. So the only time page server actually will have to read from storage is if you lose both page server replicas unexpectedly. Right, so then it has to seed that 128 gig file, and even when it's seeding in large writes, right? So seeding is not that slow, but like I said, I mean, we have two page servers, so both have to unexpectedly go down, because if it's maintenance or something which is expected, the moment one goes down or we know one is going down, we spawn another one to take its place and it services requests. And at that point, like I said, compute maintains a quality of service to both 1 and 2. So if 1 unexpectedly goes down, 2 is serving all the requests. And then we spin up another one and seed it. And once it's seeded, then it joins kind of to, from a quality of service perspective. So that's the fault tolerance from a page server's perspective. Right. So I hope that answered the question. So from
yes.
a write perspective, a write transaction is generated by the primary, and all it does is it effectively, the write actually commits it to the landing zone. Once it commits it to the landing zone, it asynchronously sends it to this xlog process. We pretty much return a commit to the application. The application moves on. Asynchronously, of course, every secondary and page server asks for that log and applies it, to the contents. Now, note, if you're reading a page in primary, the buffer pool already has that data, so it's not like it's going to go to the page server. A replica might not have that data if you're actually querying a recently, done change, so it'll request the page server for that, data. And then, of course, we destage to standard storage. From a read IO, it's a little different. So, like we said, you have long-term retention, which is the file snapshot. Initially, when we spawn a new database, totally, yeah, the page servers are seeded from this, data file. But once they are up and running, I mean, everything is serviced from here or here. So if a user application does a read request, effectively, so if the data is in buffer pool, there is no IO. It's no different than kind of your standard SQL server. If it's not in buffer pool, it'll look up RBPX to say the local cache, which is local SSD cache. That's not covering. So it's only size the RBPX cache on the compute, primary or secondary, is 3 times the amount of memory for that tier. So if it's an 8-core 60 gig memory, so it's 3 times 60 gigs. So whatever that math works out to be. So if it looks up the data and finds it in RBPX, it never goes remote. So it'll service that. So if it's in buffer pool, it's local. If it's RBPX, it's local. If not, it's considered a cache miss from a cache perspective. So it then goes to the page servers, and it knows, because it knows what page it's requesting for. It knows what page server to go to, right? Because the IO is on a specific file, and there's a mapping between file and page server. So it says, give me this page at this particular LSM. If this page server already has that page at the latest LSN, it just returns. If it, for whatever reason, it does not have it at that LSN, then it requests the log service, hey, give me the log records to catch me up to this LSN. It catches up and returns the page. So that's kind of the thing. So any data that's hit in buffer pool is instantaneous. Anything which is hit in RBPX is in the local SSD range, 1-2 milliseconds. Anything in the page server can be more than 2 milliseconds because it's the remote IO, right? But all these caches are LRU, so the most recently data should be in cache in a way, or you know. So having said that, let's move to a demo. I am going to, let me look at the time. Not always the best. The time management. Okay, so I'm going to actually switch. Let me switch to the portal first. I have a database which is hyperscale here. You will see the tier right here. It is a Gen 5 generation 16 core database. There is no limit on size. Actually, we're changing this. This UI of percentage has confused people because you feel like, okay, 46, I have only 64% left. This is just a percentage of use versus allocated. If we reach the 7 terabytes, we will grow. And then you have the concept of replicas. So adding a replicas is as simple as, by default, we create with one replica, but you can create with 0 or up to 4. And right now, the size of the replica is kind of the same as the size of compute. There's no possibility of having something different. So having said that, I am going to actually switch to a demo of Readscale. Actually, before that, let's look at a few things. What happened to my view? Oh, this is the wrong one. Sorry. Okay, Solution Explorer. Let's look at a few in internals, right? So, as you said, how many page servers do I have? I have as many as number of database files. So this is, the Systar database files is kind of the standard thing, right? So you see which one is log, which one is data, and you see all of them are 128 gig files except for the log, which was more of the landing zone, right? And as you scroll down towards the end, you'll see those end ones actually not all of the data is allocated. I mean, so it's allocated but versus used, right? So these have data, left. But once we reach 80% of the file, will spawn a new page server. So you never have to manually grow this file or worry about it from that perspective. Okay, so the rest of the weights actually will wait. We'll wait for the demo because that might be better. I'm having trouble. Okay. So, okay, let's go to this demo here. Okay, so in the demo, I have a workload I'm going to actually launch. I'm going to have, effectively 100 threads doing some level of operations. I have, some operations in this database. So just for ease, I'm going to launch that and we'll look at kind of the workload and pattern. And so while that is spawning, I know that this workload is going to actually max out usage. So what I'm going to do is, I'm going to scale this. And so I'm going to actually add a replica and we'll see how long this takes in a second. So I'm going to scale this from 0 to 2, from 1 to 2 replicas, and I'm going to apply. And then while this workload, okay, this is already ramped up, it's all green. So let's go to a dashboard, and this dashboard is based on Telegraph. If you're not familiar with Telegraph, I can share a blog at the end of this. Telegraph is an open source plugin, has some collection for Azure SQL DB, which is a little richer than currently what you get right out of the portal. You can also use SQL for monitoring on the past level, also has log analytics. It's just the delay into log analytics is a little more than the delay into Telegraph. So I'm going to show Telegraph just, because it makes it easier to demo from that perspective. So I am going to show telegraph, and you see pretty quickly, I am only going to primary here. My application intent is not set to read only. So I have 500 batches I'm reaching per second. This is just 16 V core. And I'm maxing out CPU pretty quick. Right, so a couple of things you're going to see in this, and we'll see the DMV behind this. Every tier has a set of limits, right? So this is Hyperscale 16 core. Total storage currently consumed, we won't worry, actually I have to fix this dashboard. The memory is 83 gigs for this tier, and you have a max log generation rate of around 100 Mbps. And IOPS for the local cache, local SSD is set or governed to 64,000. Right, so we see pretty quickly that this is hitting cap on CPU, right? So CPU is the one which is actually at 94% here. So it's not any other weights. If I look at my weights dashboard, I don't really have, I have async network IO, which is client is not fetching results quickly, but that's not really, I mean, it's, problem given CPU is maxed out anyways, right? So all my primary weights, otherwise I SOS scheduler yield. The average of async network IO I won't worry about, but the cumulative weights, if you see, are all SOS scheduler yield, which is an indication of high CPU. Right, so I'm going to stop that workload, and the other thing we got to see, we're hitting around 500 batch requests a second. Right, so I'm going to stop this workload, and I'm going to go back to the profile, and I'm going to add another thread group. I'm going to say this is 200 threads, right? And same thing, except I'm going to make this true, right? Read scale out is true. So what this does is appends application intent equal to read only to it. So once I do that, I launch this again. And let's see actually in the meanwhile, if my replica has come up. And we should see that that replica came up 2 minutes ago. I mean, actually, if I look at the activity log, you'd see that it's 60 seconds to actually spawn up a replica. So this is not like, always on availability group where you actually restore the database, have to seed it because primary is talking to secondary. Because of the decoupling of storage and compute, you're able to spin up a replica in roughly 60 seconds. Right, so that's that. So, oh, I didn't hit run. Sorry about that. I was supposed to hit run before I talked about that. So we'll go back to the dashboard. Actually, we won't go back to the dashboard. We'll just look at this, here. You should see the scale slowly. It would have scaled by now if I remember to hit run. So we were at the 500 mark. We are gone past the 500 mark. And it's scaling out now because you have 100 threads going to the primary and you have 200 threads going to the two replicas. So I expect over 1,000 batch requests per second once this all reaches. Will it be perfectly linear scale? It may not be, but then you can take this scenario. Oh, it's perfectly linear scale in this case actually, which is awesome. But that's because the workload is similar, right? But you could direct some level of read write workload to the primary and some level of read to the primary also. And as you reach those capacity crunch, can redirect the other parts of read only workload to the replicas. As you can see, I mean, we've tripled that workload using the replicas. Right, so stop. So Telegraph right now, the reason I can't show you is I have to actually doctor's dashboard. Telegraph doesn't have great replica support. Actually, something I need to add to Telegraph shortly. I contribute to it from time to time. So that's, you see the primary is 100%, but you have triple the workload requests, right? And now this data from a dashboard perspective, you should be able to see as well in the overview tab, or if you pull out metrics, you see the CPU has come up. It's just you don't get the detailed counter views, which I'll show you more in kind of the next demo. Okay, so that's that. So let's move on to a few other things and then come back to another demo. How does backup and restore work? Uh, Backup restore. So like we said, all the backups are snapshots, right? So you take snapshots every X number of minutes, let's say, for every page server, and they don't have to be synchronized across page servers. And similarly, the log. So this is the data part, and the log has this landing zone. Um, and the long-term storage. So that's where log is. So there's no log backup per se required. And the backups have no impact to the apps. Right? So say you want to restore it to a point in time somewhere here in the middle. So what you do is we take the last snapshot from each of these page servers, and they may not be at the same point of time. That's okay. And then because we have this accelerated data recovery, I hope you've heard of this with some of the SQL 2019 talks. So ADR, or accelerated database recovery, is used also by default on Azure. And in all the scenarios where you had those long running transactions and your server went down and came up and recovery took forever, that's the thing of the past with ADR. So rather than going back to the LSN of your oldest transaction, we go to the start of the LSN of the latest snapshot with ADR among all snapshots, right? And so then you have to recover that log from that point till current point of time that you've requested that restore. So the way we do that is we provision, you have the snapshots. So the snapshots actually being in a storage account is a matter of less than a minute or seconds. So irrespective of if it's 2 terabyte or 5 terabytes, the snapshots are restored in very little time, right? And that area of log that takes a little longer is copied to a parallel landing zone blob created for this restored database, right? And this is parallelized. So all these snapshots are parallelized, from the copy perspective. Right? So you have constant pitter or point in time. Then we provision the compute required for page servers, and then we start seeding it from those snapshots in parallel, right? And then, sorry, I said landing zone there, but the long-term storage active part, if it's not in landing zone, will be copied to long-term storage. If it is in landing zone, will be copied to landing zone. Right? And then primary compute is spun up, and then primary compute just recovers that tail of the log. So irrespective of size, because of ADR and because of snapshots, I would say, P90 plus or P95 plus is in the 20 minute range for restores. Are there some which go to 30 minutes? Sure, there would be some, but many of them finish in the 12, 15-minute range, even for 5 terabytes. Okay, so let's talk about migration next. Um, so migration is not is super great story all up in Azure SQL Database if you're coming from on-prem. Now, if we talk about managed instance, I'm just covering the database part of it because Hyperscale isn't available today on managed instance. It will, but it's not there today. So there is no database native restore because all your compute and storage are on, the hardware itself is not private to you only. It's not in your control. And so there's some security concerns around kind of restoring a backup which is brought from on-prem. Right, so native restore is not supported, but you have migration options. Azure Data Migration Service, there are links in this, is one way to go. The other way is roll your own with Spark, which has a bulk copy connector. There's a SQL smart bulk copy sample app, which actually bulk copies. You can just point to a source in the destination database and it'll copy all your data, and then you create indexes after that because data ingestion is faster without indexes. Or you have the Azure Data Migration Services, right? So in the bulk load, if you're using any of the bulk load, scenarios, if you're using clustered column store, bulk load directly into clustered column store. Otherwise, consider bulk loading into heaps for larger tables, or create just the clustered index, not all your indexes, because that will slow down kind of the bulk load. And then the other way is transactional replication, where you can have a snapshot, and then have a subscriber. That is just that transactional replication has a few limitations, like you have to have primary keys on source table. So, a little bit of schema dependent from that perspective of if you can use this or not. Migration from other SQL database tiers actually is just a service objective change. So you can just go to the portal and say, migrate to hyperscale, change your tier to hyperscale from business critical or from general purpose to hyperscale. Migration is done online. So what we do is we spin up new compute and storage accounts and start seeding that. Of course, that's the size of data operation. But you can use your primary database while all that background operation is happening, even if it takes a couple hours. So intense write workload, I mean, do it during a quieter time. The reason why is not so much for the initial seeding as much as it is for the catch up, because every log record that you're pushing into the system has to be applied there, after the initial seeding is done, right? So try to avoid an intense write workload perspective. Currently, you cannot go to a prior service tier, so migration to hyperscale is a one-way street. We are working on something to be able to go to a other tier like general purpose. If you go from general purpose to hyperscale, and the fundamental reason today is the storage is so different. But even when we allow you to go from hyperscale to not and not, uh, it's the size of data operation because the storage format isn't the same, right? There's the concept of page servers and so on and so forth. But you can restore to a point of time before migration, right? So if you have a retention of 7 days or 30 days in general purpose or business critical, you can restore to a point of time in that tier before hyperscale today, right? So if we said 128 gig page servers, if the source database today is greater than 128, we land on little bigger page servers. That's generally not a problem, but just something to note in the 128 gig to 1 terabyte. There are two sizes of page servers today: 128 gig and 1 terabyte. New database is 128. Old database that you're shifting tiers depends on the size of the database, because we don't reorg the data in a file. So if a file is greater than 128 gig, you land up on a 1 terabyte page server, right? So the reason why is 1 terabyte page servers can cause, if the write heavy workload, they're bigger blobs. So you can see in edge cases, really, I mean, I would say very few customers have seen, perf degradation if you're migrating with existing large databases that land on 1 terabyte page servers, and you have a pattern generally of small and lots of writes into those 1 terabyte files. Now, note, as the database grows, you get 128 gig page servers. So it's not like, the new ones aren't, 128. And we are working to address this too. So perf and diagnostics. Let's look at perf and diagnostic characteristics. So you have max log generation rate of 100 Mbps, irrespective of compute size. You may require sufficient compute. So you won't achieve 100 Mbps log generation rate with 2 cores. Unlikely. So you might need 6-8 cores before you actually hit 100 Mbps. That's 360 gigs of an hour. Scale up, scale down, latency is quick. Temp TB and RBPX are finite resources because every compute has an amount of RBPX and temp TB. So remember that to some extent. Right? Size is proportional to the number of cores. We have a limits link in the next slide, which indicates that. So for TempDB contention, in terms of GAM and SCAM contention, any of the logical contention, you can use memory optimized table variables, just like you can on-prem or anywhere else. That's a good tip if you're hitting GAM and SCAM contention. Some tips in terms of kind of index builds on the cloud. So the cloud is, so we have patching cycles every 6 weeks, right? We roll a train through QA stage and then deploy to different sections of regions, just continually, one after the other. So every 6 weeks, you will have, a failover from one node to another while we patch bits, right? And there are some previews of maintenance windows and things of that nature. But think of you building a big index on a 2 terabyte table, and you happen to fall on a window which has a 10-second, failover. So use resumable indexes for that reason on the cloud, because that enables you to just resume from the point that you were, and go on forward. Besides, I mean, on other tiers, resumable indexes also a good reason because they don't tie up temp DB as part of one transaction. Right? Max stop is another thing you might want to do to uh, create or rebuild offline indexes in particular, because the memory grants associated with that will be smaller. So up to 16 is what I would kind of suggest. The other thing to remember is replicas in hyperscale are asynchronous, so they're not synchronous. So if you're banking on data, the moment you insert a record, you're banking on that value being returned, and you can't even do with a couple millisecond delay, then read from the primary, because that's the only guarantee from that perspective. You're reading from the secondary, it is asynchronous. And on replicas, just like always on availability groups, we use snapshot isolation. It is consistent as of a point of time, but it is not synchronous. Even in a synchronous always on availability group, what is synchronous is log commit. The redo is not synchronous, right? So redo is anyways asynchronous from the perspective of a read. So be wary of that from that perspective. And some operations are size of data. So for example, if you're copying a hyperscale database cross region, or you're doing a geo restore cross region, that is going to be size of database, because there is no snapshots are only within a region. Snapshots are not cross region. Okay, so some resource management, 40, 44 minutes. Okay, some resource management thing. So and this is not only true for hyperscale, but every database service objective um, in Azure has a set of resource limits, and that's so that because it's a multi-tenant system, so if you're not using the max of 80 cores, we have multiple databases within that same node. And each database has its own instance, so it's isolated, and so are resources, and so they're capped, right? So these two links have what those limits are depending on tier, and that allows us to give you a balanced database as a service experience without noisy neighbors, and adhere to SLAs, backup, HADR kind of facets that you get for free with the service. Right? So investigating performance, the first step is to check resource usage, right? The only difference in resource usage in the portal as well as the DMB, which we'll talk about in the next slide, is the data IO percent is only for the RBPX IO. Remote IO reads are not governed, so you don't have that limit from that perspective. So it can be a bit misleading though when you see data IO percent of maybe 20 or 30, and you still see a wait tab which is page IO latch related. So performance tuning in Azure is very similar to on-prem. So I'm just giving a high level. I'm not going to go deep into this at all. Check resource consumption, and is my resource bottleneck CPU bound or any other weights, right? So DMDB resource stats is the DMB which gives you this. And then if it's CPU bound, then you go through tuning queries, figuring out what queries consume that CPU, whether it's compilation or execution. If it's compilation, means you have a lot of ad hocs, you got to parameterize it or create stored procedures. If it's execution, then tune the query plan. But you have query store, which is enabled by default. You have procedure stats and all the DMBs that you know and love. From a weight stats perspective, depending on the weights, then you take action, right? So, but again, from the weights perspective, you'll still use query store for weights, or to identify queries which are most weighting on that type of weight, right? So a couple distinct things to hyperscale on weights are these following weights. The first one is actually true of all tiers, there's log rate governor. So if you exceed the log generation rate, we will throttle you. And the way you'll see is log rate governor. The next 5 are purely hyperscale related: RBIO, RG storage, dstage, replica, local dstage. So effectively what that is doing is that is the log generation, which is 100 Mbps on primary, is being throttled because one of these page servers or replicas is behind. We don't let it get too behind. If it's over 1 gig behind, and there's some throttling algorithm around that, we will throttle log generation rate on the primary, and these are new weights that you could see. If you're pushing 100 Mbps constantly and exhausting resources on secondary, where it's not getting any cycles from resources to redo resources, to redo that workload, so on and so forth, right? Other than that, traditional weights are still here. There's a good article on hyperscale specific performance diagnostics. I have another demo, but I'm going to run through all the slides and come back to the demo. So I leave some, questions, some time for questions. IO counting, we talked about a different IO component here, which is called RBPX. So where do you see this IO? Effectively, this is exposed as DB-ID0, file ID0 in virtual file stats, right? And that DB-ID0, file ID0 is RBPX. So if you take 2 diffs of virtual file stats, which I'll show you in a second, you can get, your IOPS and your MBPS and your latency for RBPX, and for other files, right? So that's one thing. So IO bursts also get governed, not just IOPS. And then the other important thing we talked about, kind of not all your reads are local. Some of them are remote, right? So how do you guys see if your query is actually reading local versus remote? Or what if the query took longer at one shot and it's faster the next time, right? Your typical, my query ran fast, now it's running slow. Remote reads are an important part of diagnostics, and there is a page server reads column added to all these DMVs. Exec request, query stats, procedure stats, query store, and even query store. And even the actual execution plan actually has how many of these reads were paid server reads versus non-paid server reads, right? Your logical reads. So in figuring out kind of if my slowdown was due to IO, due to remote reads, this is an important metric. So let's go to a quick demo, and I'll switch machines. So I'm going to actually go through this relatively fast. So all I'm doing here is bulk insert. So I'm data loading, a bunch of data into a file. It's the same file, just multiple files into the same table, right? And right here, so I'm doing it on general purpose, and I'm going 4 processes. So I'm going to start this so that we can actually look at. So I'm going to start this, and I'm going to start the equivalent on hyperscale also, so that we do it in parallel. Actually, I can't because this one's going. Okay. Let me go to my dashboard here and switch to the hyperscale database which I'm loading into. Actually, the general purpose one. And you'll quickly see that log generation rate here, log write percent, has gone up to 100, right? This is log write percent. It's 173 average, but the max is kind of 100. If you give it a second more, it'll be 100. Okay, there you go. And this is a performon counter I'm pulling from sys.dm/os performance counters. If you look at this screen, how much log I'm generated is pretty much capped at the 30 Mbps mark. And that's because general purpose has a max log generation rate of 30 Mbps, right, for this tier. So we can see if we go up here, the max log rate is 30 Mbps, right? Same tier, same size hyperscale database. I am going to actually do that. And you'll see, I mean, this will finish in less time, but I have 8 parallel loads going. It's not just, 4. So I'll switch to the dashboard real quick and go to Hyperscale, refresh. Hopefully we get there. To start, it started. That take a few seconds. Okay, log generation rate is already gone. We'll give it a second. Okay, that's because it's not even, I mean, it's not even at the log generation rate. Log write percent is not even caught up, right? But we'll see, I'm running out of time, but we'll see log generation rate actually pretty quick here go to way more than 30 Mbps. It'll cap out at around 90 because my workload doesn't push it anymore. Right? So we have 90 Mbps of log being, written, and these 8 streams should finish in less time than the 4 streams actually go. So yeah, log write percent is around 72 now. And I mean, so you see, I mean, so and this is just with 8 cores in both cases, right? So it's not different from a resource usage perspective. So it's way better price performance ratio even from that perspective than general purpose. So other data loading things are the same as on-prem. Just remember when comparing to on-prem, it's full recovery model, right? So don't compare it to simple recovery model when you're not logging anything. There'll be a delay. Loading into column store, you can get much more squeezed in at 100 Mbps than not. And then a bunch of other, tips for partitioning for large tables is very important for switch out as well as ongoing maintenance because you can rebuild a particular partition as well as perf if it is aligned, right? And then for data load perspective, like you saw, I went 4 streams or 8 streams. Load data in parallel because it improves throughput, right? Like a single bulk insert is serial. So you will get only so much. You're going to land only on one core, doing that IO that a one core can, right? And then use a engine which is separate because it's expensive to use SQL to bulk load or bulk insert a file because SQL has to read that file and then ingest the file. So if you use ADF or Spark to read the file and just send it as a bulk copy stream, you'll even get better throughput. Right? So last but not the least, I have kind of some of the roadmap slides. We have some features which are missing slightly, and all of them will end up in the next few months. So change tracking just went GA in April, and this is parity with other SQL tiers. Right? We have TDE with bring your own key or customer managed keys, which is now in public preview. We have the database copy. Point in time restore is there today, which is GA. But database copy to a different subscription or to copy to a different region is in private preview. To a different region, you can geo restore today. You just can't use the database copy, which you see in portal. Then you have active geo replication if you want a set of primary and replicas in one region, a set of primaries and replicas in the other region. That's currently in private preview. And then we have ongoing perf improvements and a feature called name replicas, which are also in private preview. The name replicas allows a replica to have a different tier than the primary, and you be able to connect directly to that replica, not just using application intent equal read only. You being able to connect, and the idea around it is to have different security model for a replica in time, right? So that's where we are. Experience Hyperscale, that's some of these. My email is denzilar at Microsoft. My first name, first letter of my last name at Microsoft.com. If you have any questions, I should have put my email. I'll put it on the slide before I share it. So any questions at this point, I'm happy to take. Let me know.
Thank you, Denzil. We don't have any questions yet. I will certainly throw the floor open. For any of the attendees, you're welcome to unmute yourself and ask any questions of him that you may have.
I know it was a rapid pace, went through a lot, but feel free, or if not, I mean, if offline you're doing any POCs with customers or yourself and have any feedback, absolutely happy to help. So making myself available for that.
Okay. Uday would like to know if you could share the GitHub link to try the code.
Absolutely. Will do.
If you could just drop that in the chat,
Yep.
that would be
Azure
useful.
SQL DB monitoring telegraph. Will do. Yep. Okay, this is the next one actually. Yep. I will put it in the chat.
Thank you.
Chat. How do I put it in chat? Okay.
Expand the chat and then
Okay, to
select
all participants, right?
all,
Yep.
all entire, yeah.
Sounds good. If no questions, thank you, folks. Appreciate your time. Have a great remainder of the SQL Saturday or weekend.
We're done. We're
Oh.
done. That's the good news. No, I know. It's
Awesome.
been a long day for the moderators. So the final notes. Thank you very much, Denzil, for doing the presentation, and also thank you to everyone who attended. There is the SQL raffle will still be open for another half an hour. Then it'll be closing at 5 p.m. You'll be notified via email if you are a winner from any of the drawings. We don't really have anything else to really close it out. The VMware room is kind of the failover for the 4:30 to 5 p.m., but I honestly do not think we have anything more to share with you. I thank you all very, very much for attending and have a beautiful weekend. What's left of it. Bye-bye.
Awesome. Bye.